In this video tutorial, we'll see how to implement a queue from two stacks. So let's compare the properties of stack in high level, stack and queue. So stack operates in the LIFO fashion, that is last in first out, whereas queue operates in FIFO fashion, first in first out. And some of the operations that are supported by stack are push, which would add the entry at the topmost position of the stack, and pop would remove the topmost entry from the stack. Top would return the topmost entry from the stack without removing the entry from stack, and empty would return true if the stack is empty, otherwise returns false. And coming to the operations supported by queue, we have enqueue, dequeue and empty. Enqueue would insert the entry into the back of the queue. Dequeue would remove the first entry from the queue and then return it, and empty would obviously return true if the queue is empty, otherwise it's going to return a false. So now that we know that we have two stacks given to us, so let's consider the first stack as old stack and then the other stack as new stack, right? So whenever there is a enqueue, so we need to insert that value into one of these two stacks, right? Let's assume that any new entry that comes to the queue would be pushed into the new stack. So in that case we can assume that, so let's take some three values, right? So three values are inserted into the queue and it looks like this. Fine. So the bottom line is, anytime there is a enqueue, we are going to push that entry into the new stack. And as far as the user is concerned, so he is going to assume a picture like this, right? He has a queue and he has inserted entries like this in this fashion. And the queue goes like this. And whenever there is a queue is serviced, so we are going to print the 10 first, right? We are going to process the 10 first and 20 next and so on. So which is FIFO, right? So now how about dequeue, right? So we just saw the enqueue. How about a dequeue? So if we are to directly remove the entry from the new stack and then return that value, which is going to return 30, but the expectation from the user is 10, right? So obviously we cannot directly pop entries from the new stack and then return it. So we can probably use the old stack for that, right? So let's say we decide that anytime there is a dequeue, so we are going to pop all the entries from the new stack and then push it into the old stack. So if we pop out, so the 30 is the first value that is going to come out, and then which would be inserted into the old stack like this, and then 30 followed by 20 followed by a 10, right? So now at this point our new stack is empty, and then we can kind of decide that anytime there is a dequeue, we would only remove entries from the old stack, not directly from the new stack, otherwise we will not be able to meet the FIFO logic, right? Okay, so now we would pop the entry from the old stack. Now we would get a 10, right? If we pop from old stack, we would get the value 10, which is the expected result, because as far as the user is concerned, it's a queue, so he inserted 10 first and then 10 comes out first. This is good, so far so good. So we have seen how to enqueue, how to dequeue. This looks fine so far, right? So and after popping out, our new stack would appear like this. We would have 30, we still have 20, and then our new stack looks like this, which is empty now. Let's assume, right? Let's assume that there is a new entry now. New entry, so which is so this is already gone. So now there is a new entry. So as far as the user is concerned, so he is trying to push a value 40 and then let's say a 50. How that would affect our internal state of the stacks? Let's see that. We have 30, we have 20. Okay. So now that since we decided that all new entries we are going to push only into the new stack, right? 40 would be pushed first, followed by 50. So now the trick follows, right? Trick comes. So how to do a DQ now? Let's say if there is an attempt to DQ now, what do? Both the stacks seems to have some value. Should we decide to should we move all the entries from the new stack into the whole stack and then remove the top entry, or how do we do this, right? So let's assume we are going to move all the entries from the new stack into the right. So if we decide we are going to move all the entries from the new stack into the old stack, so this would look like this, right? 50 would be coming first and then followed by 40. And then if we remove the top element, top is 40, and then if we pop out, we would be removing that from 40. But as far as the user is concerned, he is expecting a value 20. So this operation is wrong, right? Obviously this is neither LIFO nor FIFO, so this seems to be totally a different data structure, right? So which is not the expected outcome. So we cannot do data movement when there is some entry available left out in the whole stack. So now we understand that. So now it kind of moves us to a strategy that whole stack can only be filled when that is empty, right? So coming back to this old state. So let me redraw that. So this is how our old stack looks, and this is how our new stack looks. Okay. Now there is a attempt to DQ. Okay. How about we DQ we pop out elements directly from the old stack, right? So we seem to have a 20, and this is the expectation as well, right? So we seem to have 20 in the top of the old stack, and from the user point of view as well, he would expect a 20. So we can start popping directly from the old stack. So obviously we need to do a top which would return 20 and then followed by a pop. So that would remove the entry from the stack, right? So that would leave the stack like this, right? We have a 30, followed by we have 40 and 50. So as far as the user is concerned, so he has also got 20. So now these are the remaining entries that are available in the queue, and internally it is stored like this. The user which he will not be obviously aware of that. That is our design goal, right? So now so far so good, right? So we have addressed DQ, we have addressed NQ, and empty is obviously if we need to find a way how to find whether the queue is empty. So when the queue would be empty, so it is possible that one of the two queues can be empty, and then the other could have values. It is possible that there was a recent DQ when the old queue was empty. We would have pushed all the entries from the new stack into the old stack. So that way, we would have only all the entries in the old stack. That is a possibility. So in which case the new stack would be empty, and this would have all the entries of the queue, right? So even though so that kind of makes us understand that one of the queue could be empty, but one of the stack could be empty, but that doesn't say that our queue is empty. So we can say the queue is empty only when both are empty, right? So we can check for check whether new stack emptiness, and if old stack is also empty, right? So we know that we can return true. Otherwise false, right? This kind of actually addresses the empty function as well. Now coming to the complexity part, any typical stack implementation would support push, pop, top and empty operations in constant time complexity. On the similar note, enqueue, dequeue, empty, size functions actually on the queue should be supported in constant time. But if you notice our dequeue functionality, we seem to do some data transfer from new stack to the old stack, which kind of looks like a order of n time complexity. But if you closely observe, we don't seem to do this data transfer quite often. Only when the old stack is empty, we refill old stack from the new stack. So on an average, the dequeue functionality still works in constant time complexity. So this kind of ends our first part of this video tutorial. So please watch the second part of this video tutorial for a C++ implementation of this problem, and part 3 would explain the Java implementation of this problem. If you are not subscribed yet, please subscribe to this channel so that you can watch more videos. Thank you.